All right, let's start. So today we have James. James is an engineer with a passion for fast computers. He's currently at James has been deeply involved in the creation of several of the world's fastest computers in the last few decades. He has authored 10 books related to parallel programming and performance optimizations and tuning. And today, James is very focused on heterogeneous computing, which he describes as the next logical step in computer evolution. Hi, James, and welcome.
Thank you.
Yeah, thanks for coming. I really actually, I really, glad to have you here today. Um, and I should say, it's a very impressive bio.
Thank you.
Yeah, so we actually were working with James on the DPC++ compiler project until recently. I joined another team, and I should say that James is really a truly vision. Like he was he actually is supervising and blazing the trail for this great project, and so yeah, I'm really excited to talk to James.
Yeah, I'm excited to be here too. Parallel programming caught my attention decades ago, and I thought it was a rather esoteric topic, but it's become very mainstream since it's a very critical part of getting performance out of the machines, which has always been my passion. So it's a lot of fun, and we've got a great head.
Sure. Yeah. Right. Before we start, let me. I think it actually will be important for both of us maybe to make a small disclaimer. I don't want to bother you guys with all this, but just wanted to say maybe it's important for us to say actually work at Intel. And I guess the thing here is not represent the official position of Intel. It's just all our thoughts, right, James?
Yeah, absolutely. Yeah, it happens. We both work at Intel. We encountered each other otherwise. I'm aware of Dennis's podcast, or sorry, Twitter chat. Um, and but yes, we're here to talk about performance and technology and technical things, and um, not state any positions for Intel.
Sure. Okay. So now that we said that, let's talk about the fun things. Okay. So let's start with with how about you, James? Tell us about like what is parallel computing, and in what dimensions of parallelism one can scale their program.
Yeah, absolutely. I mean, parallelism's everywhere around us, and we sometimes forget exactly what you're talking about. There's lots of dimensions to it. People will throw around terms like scale up and scale out, and honestly, I often forget which is which. One of them is the idea of making an individual device, your local computer, more powerful, and the other one is to uh, string together more of them. I think that's scale out. Um, it's each one of them has a lot of nuances. When we look at a particular thing like a device, a CPU or a GPU or an FPGA, there's a lot of opportunities for those devices to have parallelism in them. It used to be processors would fetch an instruction, decode it, fetch its data, run the instruction, write the results out, and then fetch the next instruction. So the first step was to make these devices fetch more than one instruction at a time, and we're definitely doing that these days in every device. In in a huge way. So the superscalar capabilities, the abilities to fetch multiple instructions, or for a single instruction to operate on a lot of data, that's one form of parallelism we don't want to miss, and that's really been driving performance in all devices. CPUs have things like AVX 512 that operate on a lot of data at once. GPUs at their very fundamental capabilities are all about operating on a lot of data in parallel. In fact, all their performance is derived from that. If you can't feed them a lot of data, they're not going to give you very interesting results. FPGAs take it a little bit different, but also have to operate on a lot of data or functionality in parallel. So you've got parallelism on the device, and then you've got the challenge that you can string a lot of devices together. Um, And I think we take that for granted now. Um, uh, I'll date myself a little, but I was one of the architects on a machine called ASCII Red, which was the first teraflops machine. And one of the very significant things there was it demonstrated that we could string together 9,000 CPUs and it would actually give you performance. And before that, there was a big argument about whether we just needed to scale up individual devices and only have 4 or 5, 8 of them. That was Seymour Cray's view. Others thought we could scale out. So nowadays we've got scale up, scale out, and don't forget the internet. We've got connectivity, we've got data centers that can help make a device that we're holding in our hands more powerful. And so you have to deal with all these types of parallelism, and some of them are reliable. Some of them, like if you're connecting to a data center, you may have intermittent connectivity, and you have to deal with that. So there's a lot of interesting dimensions to getting performance reliably with parallelism.
Okay. Well, let's talk about what programming models are available at each of those levels that you were talking about. So like how like technically you scale up and scale out.
Yeah, you know, it used to be classically people would teach you there were two types of parallelism: task parallelism and data parallelism. And it's an interesting way to think about things. The idea that maybe you have a lot of tasks to do, you can pipeline them, you can do them concurrently and so forth. And then you've got data parallelism. The reality is data parallelism's proven to be far more important. You could debate exactly why, but ultimately it's the fact that we figured out how to exploit data parallelism far better than task parallelism. So in your head, it's valuable to think about both. If you've got a lot of tasks to do and you can pipeline them and so on, you can set up a very useful structure in your head. But I would say if you're starting to think about how to exploit parallelism, the most productive thing to do is always think about where is the parallelism in your data. And what that means is how much of your data can you manipulate in parallel, meaning at the same time, being dependent on the outputs from other manipulations. So I think data parallelism is very key. When you look at it from a classic computer science standpoint, you talk about Amdahl's law, and for a long time, Amdahl's law was cited as the reason we couldn't build supercomputers out of thousands of microprocessors. Now, John Gustafson came along and wrote an influential paper, rethinking Amdahl's law. And basically what he said is, it's true that if you have a small problem, you can't infinitely make it faster. But what really happens in life is we tend to make our problems larger, meaning operating on more data. So it kind of reinforces this concept that the parallelism's in the data. So you really need to look for problems that you can scale up the size of data and that you know how to operate them on parallel. So to me, that's the most important thing when you're thinking about parallelism, is to figure out where the parallelism is. And the first place to look is in your data.
That's really interesting. I'm getting caught by this thing that you said. Parallelism is in data, and that's, I think, a really cool way to describe it. Yeah, that's really interesting.
Well, I worked with a book I did a few years ago called Structured Parallel Programming. I worked with a couple of amazing engineers, Mike McCool and Art Robson. And when I had written a book earlier, I had written it and talked about task and data parallelism. But I was writing the intro to this book, and I went to them one day and I said, I don't even believe in task parallelism anymore. Okay, that was a little extreme. I still do, but we had a great chat, and really, I think it is a fundamental moment for most engineers working on parallelism to realize that the most productive thing to do is chase the data parallelism.
Yeah, that's really interesting. All right, so but let's talk about the what are the technologies that are available at each of those levels of scaling, and can you maybe characterize them briefly?
Yeah, that's Interesting question. So, when I look at parallelism, you've got to think about how to decompose your problem, and there have been a lot of interesting tools over time to help with that. Most of them are about prototyping and characterizing your application. And if you've written the application entirely yourself, that's one thing. The problem a lot of people have is that they're working on a program that has some history that doesn't include them writing all. That's what most of us are faced with, and sometimes you need to do some experiments to try to figure it out. And there is a tool Intel has in its suite called Advisor, and it's exactly that. And you instrument the code and you try to do some different simulations on it to figure out how much of it can run in parallel. And you can do some thought experiments, switching it around. Regardless of whether you're using a tool like that or not, I'd encourage you to, before you invest heavily in restructuring a program, for real, to be completely robust and everything, figure out the cheapest way to do some thought experiments, to do, the equivalent, set it up, make sure it really works, because there's so many challenges and dependencies. And I've seen people spend months restructuring programs only to find out there was a dependency that they didn't think through. And I'm talking brilliant people who, I'm surprised by, but it happens to all of us. So modeling is much more important. If you get a good design, that's tremendous. Now, what are you trying to do? Well, the first thing you're trying to do is decompose so you have absolutely as minimal, as few dependencies as possible, that you can operate on the data as massively in parallel. The next thing you need to do is figure out how you're going to express that in a way that exposes the opportunity for parallelism, but doesn't demand that it be used. And the reason this is important is your application may run on a machine with 1 core, 10 cores, 100, 1,000 cores, right? Or your EMs on GPUs, whatever the unit is that can run for you. You may get a small number or a large number. Or if you're doing things that use vector instructions, you may be on a machine with a vector width of 16, and you might be on a machine with a vector width of 32. So one of the things that differentiates different programming models is how well do they scale. So if you take a look at a programming model that's kernel-based, like CUDA, popular, or OpenCL, or SYCL, data parallel C++, these are all kernel-oriented, and they have a very simplistic model. You write a subroutine to operate on one piece of data, and then you say, hey, apply it everywhere. So, in a really simplistic example, if I had a photo, an image, and I want to brighten it, I might want to add 100 to every pixel. Of course, I'll use saturating arithmetic so it doesn't wrap around and create dark spots on the bright spots and so forth. But, basically what I'm doing is saying I can write a kernel that says pixel plus equals 100. And then I just say, here's my kernel, run it on everything. The beauty of programming in that way is you obviously have no dependency. Every pixel can be incremented by 100 regardless of what's happening on the pixel next to me. Now that's nirvana, so things, real life get more complicated than that. And so you start thinking about data flow, you think about your problem. So you might sketch it out on a whiteboard. In your head, what's the data flow, but you're looking for as many opportunities as possible where you can say, hey, I can do a lot of this in parallel. And then there's great programming techniques. There's things like kernel-based programming is fantastic. You've got things like threading building blocks, which is very popular in C++ for expressing parallelism as well, that has proven extremely popular in the especially in the animation industry, and Hollywood uses a lot. It's used in other areas as well, because it just lets you express parallelism. If you go to some of the older techniques like OpenMP, they're much more prescriptive. And it turns out that they work well in situations like supercomputers, but they don't generalize as well. They get into trouble because they were trying to be overly prescriptive.
Right. Okay. Yeah. So can you maybe like okay? So you already started talking about all those different technologies like OpenMP, TBB, and offloading. What about vectorization? What are the programming and how users can achieve vectorization? So can you just name few technologies and maybe like describe them shortly?
Absolutely. So first of all, I'll say, there's always this question, why don't compilers just do it? Why don't you just magically vectorize things?
Sure.
And so, auto-vectorizing compilers have been around for a while, and they'll pick off the easy stuff where there's absolutely no dependencies, and they can vectorize. And vectorization just means you look at a program that was written in a sequential language. And by the way, virtually every language we work with is sequential, right? C, C++, Fortran, Python, Java. They're all, a for loop is defined as do the first iteration, then the second, then the third, then the fourth. And a compiler has to stare at that and say, hey, can I run some of those iterations in parallel without changing the meaning of the program? And that turns out to be complex. So predictably, compilers aren't great at it. They do the easy stuff. So that means that us as a programmer, we need to figure out what we're going to do. On one extreme, you could just start basically programming an assembly language. Nowadays, that would generally mean you write intrinsics, which look like function calls, but they're really mapped to the hardware. And everybody supports intrinsics of one sort or another for their hardware. But you have a few choices. Kernel-based programming is effectively vectorization. In fact, I'm kind of excited because I think kernel-based programming has been applied for GPUs for some time, but as we see more generalizations of it come out, obviously CUDA is just for NVIDIA GPUs, but if you generalize it and you have something like OpenCL or SYCL, you can start to say, hey, I can vectorize things for other devices, not just NVIDIA GPUs, other people's GPUs, maybe for AVX on Intel and AMD processors. There's equivalent concepts for vectorization in other CPUs. So I'm excited that I think kernel will actually help with the vectorization problem. Otherwise, most people rely on things like OpenMP that have directives that tell the compiler vectorize this loop. And going back to what I said, compilers are terrible at automatically vectorizing, and the reason is that all the different requirements of a language scare a compiler that when it vectorizes, it's going to change. It could change the intent of the programmer. When in reality, when most of us say parallel for, if there's not an obvious dependency between the loops, we generally are okay whatever order it runs in. But the compiler can't always figure that out. So usually what OpenMP pragmas do fundamentally is, in general, they just say, dang it, parallelize this loop or vectorize it. And once you tell the compiler, vectorize it, I'm okay with consequences, compilers can do a good job of packaging the vectorization. So usually if I'm vectorizing something in C or Fortran, I'll look at OpenMP. Most compilers support it in one way or another, and simple vectorization is pretty easy to order. The challenge, of course, is you have to be careful that you don't vectorize something where it does change the answer. You'll
Sure.
you'll learn the hard way.
Sure. Yeah, that's true. Okay. So in the terminology that you defined, scaling up means vectorization, multi-threading. So scaling up is essentially like scaling within one socket, right?
Yes.
And then so we have vectorization, we have well, obviously all the built-in features in the CPU, like out of order, like superscale and execution, right? And then we have multi-threading, and we have like we can offload to different accelerators. So this scaling out is like when we actually like do computations on more than one CPU or one socket. But now how we go about doing this?
Yeah, well, the further, and there's always an argument about where to scale out start. When you go multi-threaded or you go NUMA, is that scale out? And the reality is the more you scale out, the further away something gets, you start having issues that are predictable. You go to NUMA, you've got different latencies depending on which memory you're touching, near memory, far memory. When you go to a distributed machine, it gets more extreme. So the cost of moving data around, and keep in mind, I said the parallelisms. Well,
Right.
one of the frustrations to getting performance out of manipulating data is the cost of moving data around. So obviously you want your computation to be local to the data, and that's one of the big challenges of programming models and the way you factor your program is if you're going to scale out, you're ultimately going to distribute your data. You're going to want to focus most of your computations on the local data, and then occasionally you need to exchange data. And most programs, for simplicity, to keep our sanity, they usually exchange things synchronously, meaning you run the program for a little while, you hit a barrier, which is where everybody waits until everybody's done doing the exchanges of data. So you hit the barrier, everybody finishes their computation, they exchange a little data, and then they move forward. Those barriers obviously are the exact things that cause Amdahl's law to frustrate us, right? Because as soon as you hit a barrier, you're essentially serializing the program, and the longer you spend synchronizing, the less speed up you get. So there's a real art to understanding how to distribute your data, minimize the number of barriers you need, try to maximize the overlap of exchanging data with computation. It's easy to say all these things out loud. I'll tell you, getting into the thick of it and doing it, nothing's better than experience. You really just go at it head on. I think your speaker a couple of weeks ago said something very that really was near and dear to my heart. Something about the difference between someone that's really good at performance tuning and someone that's not is tenacity, was it? Or they never give up. And I can say the same thing about parallelism. There isn't some magical formula where some people are more brilliant than others. I think it's a lot of tenacity and just experience, and it'll sink in over time if you figure out why on earth is my program not scaling up. It's all about it becomes all about whether you're manipulating data locally.
Right. But so given all those dimensions of scaling, which one do you think is more important, and which would be approached first?
It's in this day and age, so many problems need to scale out, need to use more than one core, more than one device. I would say I would focus on the scale out first for most large problems. Now I'm biased because I tend to work on very large problems, but I remember working with some folks at DreamWorks probably a decade ago. They were working on some of their movies, and they had 24 core systems at the time that their animators used. And we wrote some articles together about how to parallelize. And one of the things that really struck me was that they didn't talk about vectorization. And I asked them about it, and they certainly did vectorization, but they were answering the question you just asked, which is, what do you think about first? And it was, well, we need the 24 cores efficiently. We need to lay out our data and so forth, and then we'll see what's running on the individual cores, and we'll make advantage of them optimally. We'll optimize the cores, and that includes vectorization second. And the reason is the vectorization it gives you a fixed amount of speed up, whereas the scaling out, 10 cores, 20 cores, 24, you can continue that, whereas the boost you can get from vectorization is fixed. Now, the benefit of doing both at the same time is huge. You don't want to ignore one or the other, but I would
Right.
definitely say scale out first is the technique that I think most experienced people eventually settle on and find to be most productive.
Fair enough. Felipe, you wanted something to say?
Yes, first of all, James, thank you for your time. It's really exciting to me to listen to you. I have listened to you for a while, a couple of years ago, and today I have opportunity to talk to you directly. So my question is, there is people that have been work on identifying bottlenecks in parallel, kind of accelerating them, for example. Mostly divide them in two parts. We have the serial. It's just look at the Amdahl's law, and find out they have the serial part, and there is a bottleneck on this part, and also they have some kind of bottleneck in the parallel part that this formula doesn't take in account. So people have trying and applying different techniques to accelerate this bottleneck. One of them is using heterogeneous cores, where a particular core that is for others, and you have another small ones that you use for parallelism, and you use the big core or the fast core for the big for the serial part, and for the large, for example, synchronized code, for example, where multiple cores will try to access, for example. I want to listen to your experience in the field, how people is fighting, for example, bottlenecks in parallel program.
Yeah, it's a big and interesting topic, and glad that you're here. Yeah, big and little cores are an interesting one. I worked on Xeon Phi from Intel, which was an amazing project where we took small cores that were really stripped down. They couldn't do as much per core, and put a lot more of them on a die, because no matter how brilliant your designs are, you're constrained to the size of a die. Although these days with chiplets and stuff, that's becoming fuzzier and fuzzier. But and when you get a program that's truly written to take advantage of parallelism really well, you will get more performance if you have smaller, less capable cores and more of them. For a variety of reasons, when you go to smaller cores, they often run at slower clock speeds, and it's a very complicated set of different design constraints. But so it's an interesting thought experiment. Am I better off with 50 cores running at 1 gigahertz, or with like 10 cores running at 2 gigahertz or 3 gigahertz? And it turns out exactly what you were saying. The parts of your program that are more serialized and such, it's actually nice to put them on the core that's running at 3 gigahertz or 4 gigahertz, and get past that serial portion as fast as possible. But once you get into a highly parallel thing, you can take advantage of smaller cores. And not just CPUs, but GPU cores are very small, and there's lots of them. And depending on how you use an FPGA, it can be that way. Most ASICs for AI and such are centered around a lot of little, simplistic computational units, and lots of them. But you really did point out a key thing, which is when you hit that serial part of your problem, in order to keep Amdahl's law at bay and get scaling, you have to get past that serial portion as fast as possible. And programmers really focus on reducing the serial region if you have a homogeneous system. Well, with that system, it becomes even more complex, because you may have ways you can shift your workloads to different hardware, and some of that's automated. I know Some of the systems will try to automate moving things to a big core, but I'm much more of a believer in the programmer having a lot of control. So it's one more dimension for us as programmers to think about. And so, you know, when you have in the past, I've heard people with accelerators. There have been accelerators around for a long time. There have been math accelerators, you know, in the 80s and the 90s, and you know, GPUs are yet another accelerator, TPUs, so forth. And you'll hear people who design these accelerators for decades sometimes say, "Hey, this is so cool. We don't need a powerful CPU." And the reason that they're always wrong is exactly what you're talking about. If you have a really powerful CPU, you can get serial bottlenecks faster and your program scales better. The IBM Cell processor had a similar thing. They had some amazing accelerator units on it, but their people who programmed it eventually felt that the control logic was too slow, and it couldn't feed the accelerators as well, but it also just didn't get past the serial portions as fast. So when you architect a machine, you have to find a balance that matches your program. And today that still tends to mean whatever's doing the main control logic of your program needs to be pretty fast. It's not enough just to accelerate the parallel portions of your program. So it's, I'd say it's a bit of a black art. You get used to it after a while, but when you're trying to speed up a parallel program, you're really hunting around trying to understand where the bottlenecks in the program are, and then you have to use your creativity as a programmer to figure out how to get rid of them. I'm fond of saying beat hardware, meaning that if you come up with a brilliant new algorithm or way to solve a problem, you can often beat advances in hardware by several generations. And I can't write a textbook telling you how to algorithm that's far better than the ones before you, but I will tell you that when people do that, they change the world. So you just have to have a really open mind about structuring your program. And then sometimes you just have to roll up your sleeves, find those bottlenecks, and do everything you can programming-wise just to trim them down.
Yes, thank you. Another part that I would like to mention, for example, talking about heterogeneity when we have different cores working on different frequencies, for example, is that is a kind of when we have these small cores working on this low frequency and we have a big one working hyper frequency, where we take large critical section on serial part of our code to send there. Of course, there is also problems there. The advantage that people have is the fact that you have locality, for example, and you avoid cache ping pong sometimes too, because there is no thread fighting to get the synchronizations or the shared data, for example, for synchronization. I mean, acquire the lock, for example, and there's also this benefit. Even when you don't get a lot of performance, you actually gain for the locality that you operating on, because it's actually only in one core. For example, and I found it really interesting also. And another point is that the contention for the lock, sometimes people have been proven so that change in a program. For example, you have a part of your program where a particular critical section is the one that the cores are fighting to get to. Later on, after maybe 1,000, 2,000 cycles, this particular critical section is no longer in getting a lot of attention for the cores, but it's another one. So people now are trying to identify this dynamically, because programs may not be aware of this change dynamically when the program is being executed. So they are trying to put codes, for example, counting the amount of cycle a particular core is waiting, and then based on they try to note when this particular code no longer need to be sent for this in this big core, but to be executed locally, for example. I would like to know your thought on what you think about these ideas.
Yeah, so you know, it used to be when we first introduced event counters in the processors, and again, this is 25 years ago. we counted simple things like hash misses and so forth. And back then, those actually mattered. But nowadays, you don't want to measure cache misses and things like that. What you want to measure is stalls, like you're saying. How long did I stall? When I was doing no useful work, because I really don't care about a cache miss. Cache misses can get serviced, and maybe the cache is fetched or the lock is unlocked before I even needed it. What I want to see is how often am I stalling. So the Intel's vTune profiler can get access to those stall counters. There's other tools out there as well, Tau, that can access these event counters. And yeah, you need to go look for stalls. Don't be misled by looking at the places where your program is doing the most computation or seeing the most cache misses or fetching the most data. You might be able to tune those a bit, but what you really need to get rid of is stalls. You need to figure out where your program, the way that it's written, is stalling. And that can teach you a lot. It can teach you a lot about the context. I think it can be very difficult to understand the implications of parts of your program in terms of stalling, asking for a lock. And then you find out that there's, what really happens is there's dirty data in someone else's cache on the system that has to be flushed and observed, and it's competing with other traffic, and it can take a while to get that lock. And if that happens very often, it can really slow your program down. There are people who look at trying to do lockless algorithms, and in general say that is a disaster waiting to happen. Every once in a while, you can do a simple thing with a lockless algorithm, but locks are a safety measure you don't want to miss out on. But what you need to do is carefully architect them so that the locks, for most of the time, aren't actually needed. So there's a lot of tuning to do there, and my favorite thing to do is get into vTune and observe with a program, where is it actually stalling, and then go scratch my head and ask myself, how could I restructure the program or do something a little different so that this isn't a bottleneck causing stalls.
So that's actually interesting. So to James, let me ask you actually a broad question here. So since you already started talking about the vTune and stuff, so what is your general approach to performance engineering? Like, do you recommend methodically go from top to bottom through the hardware and software stack, like checking each layer, or do you go from the first principles, like aka roofline approach? Or do you perform ad hoc experiments maybe?
It depends a lot on how about an application, but if I'm approaching a program that I have modest understanding of, usually I'll pull out tools like vTune to reinforce my understanding of the application, do some profiling of it, do some characterization of stalls. Where is the program spending time and where is it stalling? And obviously, if every time on startup the program stalls for a bit and then gets running, I don't care about that stall as much as if the stall's happening in some intensive part of the computation. So I will tend to try to characterize it like that. And then next thing I will do is I will try to find out the cheapest way to test my theories of how the program could be made to run faster. I really don't like recode parts of a program and then finding out I was mistaken, right? I try to figure out the cheapest way. So that sometimes that means I can go put in a few directives or make a few changes and then observe what happens to my program. Sometimes I can use a tool like the Intel Advisor which also basically has me put some macros into the code, some lines that help instrument it, and then Advisor will give me roofline models and things like that. And the funny thing is roofline models are fantastic, but they still, assume the structure of your program, right? None of these tools can tell you, oh my gosh, if you restructured your program for an algorithm, it might run 10 times faster. There isn't a tool on the planet that exactly does that. So while you're looking at all these different datas and characterizations and so forth, it helps a lot to understand what the program's trying to do, and think about, are there any other approaches that could do it just as well? And one of them is funny enough, is are you over computing anything? Every once in a while, I'll find a program that is computing something, and it's computing it to more precision than it needs to. And I know, with AI these days, so many of the algorithms are, it's kind of a race to the bottom. How little precision can I get away with? But I've also seen in scientific programs sometimes that they're over computing something, and that there are, approximation mathematical algorithms that can get them close enough much faster. And that's an algorithmic change. But yeah, I definitely characterize the program with something like VTune, a profiler, and then I go make some changes to it, and either have a tool like Advisor tell me about that. I run a profile again and then pull it into a tool like VTune that can do side-by-side differences and show me, what did my experiment do? What did it shift in the behavior of my program from one to another? And I get especially excited if I significantly reduce the stalls where they matter.
Okay. In one of your talks, actually, so James, you which are on YouTube, and I should say that there are plenty, and I actually strongly recommend everybody to watch James talks on parallel patterns. That's another great talk. So in one of your talks, you said that you should be looking for surprises.
Yes.
What kind of surprises are you looking for?
Yes, this is a talk I do a lot, and I've had the honor of going and talking at some of the national labs talking to scientists that just are so amazingly brilliant. What I'm after is there's no substitute for really, really understanding your program. So, most of us, after you work with a program a while, you think you understand it. I very proudly think I understand my program. So when I use a tool like VTune, I sometimes think about it like walking into a dark room with a flashlight and shining it around. It's okay if it reconfirms some of the things I knew. That's kind of cool. What I'm really looking for are surprises. I've seen these a lot. When you see something and go, that can't be right. Wow, that don't ignore those. Those are the things that can revolutionize your. It's where would we be if the petri dishes that were getting ruined by penicillin got thrown away and they kept running the experiments? And the penicillin eating away at things was a surprise. You're looking for that sort of surprise in your program, something that doesn't make sense to you, something that's like, that can't be, and then chase it down and don't give until you understand why something surprised you, because those are the places where you'll learn something about your program that may give you the opportunity to revolutionize its performance.
Cool. Yeah, that's great. Let me switch gears a little bit. So you were actually already started talking regarding accelerators, right? And I wonder what do you think is the future of accelerators? And I explain in what context I mean that. So I think there are many things going on with regard to accelerators, right? So as we said already, there are a bunch of them. They are different like accelerators like GPUs, FPGAs, TPUs, NPUs, VPUs, and like whatever XPUs out there. And it seems we're undergoing, trends that actually contradict each other. Let me explain. So, and I think that the market of discrete GPUs is growing, right? But at the same time, like in phones, everything is packed into one SoC. right? And also on CPUs, we have like different capabilities of doing more accelerated computing, right? So which we usually offload, like with all those SIMD instructions and recently those extension like for matrix operations, VNNI for neural network processing and so on. So it seems to me that CPUs are eagerly borrowing some of the features from accelerators. What do you think will be the future of accelerators? Will we have everything like on package, or we'll have like multiple accelerators inside one socket?
Well, of course, you already know the answer. It's both, but it's a fantastic dynamic. Floating point arithmetic, when the first IBM PCs came out, was an accelerator. It was an optional accelerator you bought and plugged in next to your CPU. It wasn't until the 486 that we brought it on package. CPUs or anything, integration has huge benefits. And nowadays, the ability to integrate stuff is crazy. It used to be kind of a big deal. Pulling the floating point unit or pulling memory management onto a CPU was a big idea at the time and somewhat controversial. Nowadays, it's old hat. But the SoCs, the ability to bring things on die is one thing, but now you've got these, and I don't know the right terminology. If people call them chiplets, whatever you call them, lots of little pieces of silicon that are connected together and then put into one package. And people are figuring out, it used to be you put them side by side and connecting them with gold wires. Now quite often you can stack them or attach them in various ways, and it's that dynamic's real exciting. So, I step back from it as a software person and say, I need to keep a consistent software view of this, regardless of what the hardware looks like. And this is really what drew me into the One API project, drew me into the SYCL standard. It's a lot of those discussions at their core are about what are the right software abstractions. So if I'm writing a program in SYCL, the key things I'm worried about is what devices are available to me, and then how do I dispatch work to them? Ultimately, if it's on package, I probably have different latencies and different access to memory. And if it's off package, it may be higher latency, and it may or may not have coherent memory. But those things are somewhat secondary. I want to structure my program with the concept it'll offload things, and that offload may come right back to the CPU to AVX512, or it may be dispatched to a TPU that's outside of my package. And I think as software development moves forward, we need to continue to have these discussions of abstractions, because the hardware is going to keep moving around a lot. We need abstractions that are somewhat stable, the concept of enumerating devices and then dispatching work to them, rather than thinking about whether they're on package or not. And if we do this right, it really, and if we do it open with a multi-vendor, multi-architecture view, we really unlock some amazing potential in hardware designers. Because I'll tell you, the hardware designers out there are chomping at the bit to throw every idea at us. And good. Unlike everything else, some of them will, fall by the wayside. I'm just excited by the opportunity to try to open things up more so that the innovation can really take off. So yeah, that's where we're at with heterogeneity. I think we're just at the tip of the iceberg. There's so many brilliant ideas out there about acceleration capabilities, and when you start talking about putting them on chiplets, that can potentially open up people that are doing SOCs or doing things where the package has multiple triplets in it. It actually gets potentially pretty inexpensive to produce multiple SKUs. They have a processing core, and some of the SKUs have some neuromorphic computing on it, and some of them have GPUs, and some of them have TPUs on them, or whatever. I think we'll see more and more diversity and we all need to be programming to an abstraction that allows our programs to quickly adapt to that and use whatever is available to us.
Okay. I don't know if you watched it, but so recently there was a talk by Brendan Gregg. It's actually from 2021, where he made a number of interesting predictions about computing industry. And there are actually many things that he said, but I just want to mention two. So first he said that multi-socket systems may disappear in the future because the single socket becomes big enough. And the second prediction that he made is that we will reach the limit of the number of cores by somewhere around 2030. And he actually said that we'll reach the limit around 1,000 cores. And so here is the where the let's say the extension of Amdahl's law, universal scalability law comes into play, right? So things like interconnect and cache coherency may become a bottleneck. So what are your thoughts on those two?
So I have two thoughts. One, first of all, the sort of concerns that he's highlighting are very real. I would never want to, dismiss them. On the other hand, the longer you work in this industry, the more you realize that most predictions of disaster, we always find a way to cheat death. So when I helped deliver ops machine, a few decades ago, people said, "Oh gosh, we don't need more than that." Of course, Bill Gates said we didn't need more than 640K of memory, and there's lots of quotes through history. Or IBM, we don't need more than 18 mainframes in the world. That's all the computers. It's people often help illuminate that it's like these are barriers we don't know how to get past, or these are things that they predict. On the other hand, I am quite sure we will find ways to cheat death. And for parallelism, for making computers more and more powerful, increasingly the key to making computers more powerful is to have more connected together. That happens both with the cloud and the internet. It happens locally. I think we will continue to find ways to scale out. The technologies we have available to us will dictate exactly how we solve the problem. And it's pretty hard to tell in 2030 exactly what all those things will be. The key isn't whether we can build it or not, it's whether we can use it. That really dictates what our computers will look like. So 1,000 cores.
Okay, sorry about that. Hit the wrong button. James, please continue.
Yeah. So the future will have a lot to do with whether we will whether we can use it or not. So really, the thing to think about is what algorithms, what can I write to use something, and if you can come up with a technique that needs more than 1,000 cores, multi-socket will live on, right? If you're limited to a single core to or a single device to 1,000 cores, it's really hard to predict what computers will look like in 9 years. It'll depend a lot on the software we develop and what type of hardware we can utilize.
Okay, thanks. Felipe, you requested the mic. Mm-hmm.
Yeah, I would like to make also some questions and also make some, I don't know, maybe contribution to some thoughts that James did. My first, for your question, when you mean for different accelerators in the same chip, I think it's a question of studying workloads, right? Because you don't want, if you know your workloads, you don't want particular accelerators that make contribution to nothing to this particular workload on your chip. Right, you need to kind of know, and I think this is the direction that we'll be in the future. People will start studying workloads, and based on a set of workloads, people will start designing computers and accelerators. This is what I think, because actually, we don't want for people to have 3, 4 computers for one specific workload, right? You don't want a computer, for example, that's only when you train a neural network, and another one when you train a different kind of workload, for example, that have a different memory pattern, different processing parallel pattern, for example. You try to put this, identify some similarity between these workloads and put the accelerators on these in these machines so they can work with different workloads. I think this is a better way to go than actually have this unique or fitting a particular architecture for a specific workload, for example. That's my first thought. And
I agree. I think you mentioned kind of two things. One is economics, and the other is well, yeah, it's usability. If you build a more general device that can do like training and inferencing, you'll have a bigger market. On the other hand, the question is, if you build a machine that can only do training or only do inferencing, it's a smaller market, but how much better can you be at it? And it's a classic design trade-off, and you're absolutely right. You can't go too far one or the other. You won't have a big enough market to sell into.
Yeah, thanks for the addition. And my second thought on the future of how a parallel program will scale, for example, I hear from an expert in computer architecture, I'm just an enthusiast, and he said that the future for scale parallel program is on-chip networking. And because they maybe find nice ways of communicating with big numbers of cores, for example, maybe this is the direction that they took. And another thing that I want to add when people defining how parallel program we scale, actually, that many people sometimes don't mention is memory, for example. The problem is we can put a lot of cores in a computer, but the question is there enough memory for all of them, right? Because we actually, DRAM memory is scaling well, right? The density of DRAM memories is a problem because the way this density scale problems are start happening appearing, for example, rotation times, for example, and whole hammer vulnerability, for example, two problems that I can mention, for example, that actually put a question if the future of DRAM memory, for example, because I think it's a bottleneck for many things, for performance, energy, and many other things, for example. And if DRAM memory doesn't scale, and looking for the future memory system that we add in the future, I don't see a particular candidate, for example, that can give us everything, right? I think the solution against heterogeneity, for example, is trying to put different kind of memories that you see and try to make them work together, for example. But I don't see, for example, how memory will scale in the future, and I think this is the major concern right now for me. I don't particularly worry about cache coherence and this kind of thing. I think they also a problem, and maybe people will try to get away from this. But my particular concern about parallel program is DRAM. I mean, I would like to also know to listen to your thoughts about this particular problem.
Yeah, absolutely. You touched on two things. One is interconnect, and I think the interconnect speeds inside a data center and on chips are accelerating, and that gives us a lot of opportunities to reconsider the role of everything in the computer's design. And so high-speed interconnects on a chip certainly are getting very attractive. And if you can do high-speed connections between the different chiplets or different portions of things on your die, that really helps. You are correct, memory is a challenge. And one of the reasons memory is a challenge is because memory is fundamentally done on a different process. It's done in silicon, but it's done in a different process than random logic. And because of that, while it's possible to put memory on the same chip as random logic, it's prohibitively expensive because the steps to do the different parts of the chip are are different, and you really don't want to take the processing time, double it on a chip. So the solution to that seems to be, again, I call them chiplets, and I apologize to my hardware friends who will probably tell me to use better vocabulary, but let's call me as soft as, hey, it's a piece of silicon. And can I glue them together? Again, not the right term, but there's all sorts of exotic things being looked at in packaging, and some of them really look like they hold the potential to have a memory chip and with a lot of pieces of memory, have a computational chip with a lot of little computational engines, and then marry them in a way that gives a little bit each of the computational units. So I think there's some relief on the way, and especially if you're willing to write a program that doesn't worry about coherence or it's some form of relaxed coherence. Because coherency, if every chip has to have the same view of every piece of data on a system, you're lost. It's hopeless. So as software developers, we have a role to play in the way we write our programs to not insist on coherency across all the data for all the devices at the same time. Just become coherent at barriers. I think there's some exciting technologies on the way in hardware. There have to be, because otherwise it doesn't make sense to make more and more computational units if you can't feed them with the data.
All right, James, let's talk about supercomputing. So this will be, I think, the topic that well, you are an expert, obviously, and we would like to know about this. So tell us about supercomputing. What are those beasts and how they look?
It's first of all, I will give a simple definition of a supercomputer. To me, a supercomputer is exactly what it sounds like. It's a computer that's really super. It's bigger and better than anybody else's computer, right? That's it. I just stop there because that allows a lot of innovation. I'm always amused with people talking about traditional supercomputing. What the heck is traditional supercomputing? You had Cray-1 vector machines, and then you had the Ps and YMPs, and those really were about scale up. And then suddenly you went massively parallel with microprocessors, and people argued that that was not traditional supercomputing. And then it turns out we figured out we can hook together thousands or now hundreds of thousands of cores, and those cores, CPU cores plus GPU cores. Now people call that traditional supercomputing. Then along comes people with ideas of doing AI, and they say, "Oh, that's not traditional supercomputing." I don't know. I'm a Billy Joel fan too, and he used to sing about it's still rock and roll to me. It's like everybody's trying to give a different name to something. It's why the heck. If I'm looking at building a big system to do lots of computations, I want to do whatever computations matter to people today, and I want to imagine the biggest computer I can that can do that for people. And so over the course of the next year, we're going to start seeing exaflop machines delivered to the marketplace. And when we hit teraflops, people said, do we need more? Then when we hit petaflops, people said, do we need more? When we hit 10 petaflops, people are, I don't think we need exaflop. Now we're going to hit exaflop. I know people who can tell me things they can't do on an exaflop. They're looking for zettaflops. It's one day we'll have enough compute power. No, we won't. And it's fascinating to me to see, though, on each step of the way we say, hey, I don't know how to build a supercomputer that's 1,000 times faster. I've got bottlenecks, I've got memory issues, I've got interconnect issues, but slowly we melt away those, and we build yet another more powerful computer. One of the greatest joys of my life has been that when I first started on supercomputers, the only people who wanted to use them or build them were governments. And those governments usually were doing things in the weapons domain. I'm very happy to say that that's a minority of what supercomputers are used for these days. It's a very small minority. There's things like weather modeling, climate modeling, pharmaceutical work, just unbelievable workloads that help the world become a better place, hopefully. People really have opened up their imaginations about what they can do with a lot of compute power. And I see that just exploding. So supercomputers are a combination of dreaming big about what I could use a lot of compute for. And people have gotten a lot more creative at that the last few decades. And then hardware engineers and software engineers working together to say, what can I build that's usable? And I'm excited to see exaflop come to life. The architectures are really exotic by any standards, and yet I think we'll surprise ourselves again 5 or 10 more years when we go to zettaflops. Probably 10 years, but we'll surprise ourselves again at the architectures we come up in our software and hardware to take advantage of that compute power, and hopefully keep making the world a better place.
I should say I'm a little bit lost in all those, and zettaflops. So let's. So can you please define exaflops? How big it is comparing to, let's say, to my workstation?
So an exaflop means that it can do 10 to the 18th calculations, floating point calculations. I don't even know these days what your desktop can do. It's probably ranged. I don't know. I numbers escape me, which might surprise you. It may be in the teraflop range roughly, which is 10 to the 12th. So we're talking about times as much, in round numbers. I might be off by an order of magnitude, but a million times the computations per second. And by the way, those computations are very tightly connected. One thing that definitely happens in supercomputers is the interconnect needs to be very strong. The memory, the storage, everything has to be really tightly linked because your computer's only as good as the weakest link.
Right. Okay. So you also said that supercomputers are now used in all those scientific calculations. So what are those guys that can afford one? And if I cannot afford, obviously I cannot afford a supercomputer to have at home. So how I can, maybe reserve the time on that user?
Most scientists and engineers get access to supercomputers through some funding program or grant or whatever that gets them time on it. Most supercomputers are shared. So they often go into universities that then have allocations, the NSF or whoever will fund the machine, but they have a very open system where they essentially charge you for time on the machine. But what happens is the charges are paid for by grants. So if you've got a great research idea and it needs a lot of computation, there's a number of places you can apply for grants. And those grants essentially give you time on the supercomputers. So if you're a brilliant scientist with a great idea, getting time on a supercomputer is something you can do. If you live in the United States, there's a number of places. NSF is one of them. There's different exceed programs and so forth. Europe has a number of programs. I'm not as versed in other places in the world, but I think it's pretty similarly around the world. Often with universities, sometimes with government agencies like the NOAA, the Ocean and Atmospheric branch in the U.S. government that looks at weather models. Definitely shares their machines with like-minded people in that. The meteorological organizations in the UK and in Australia and New Zealand have a lot of like-minded people sharing ideas about weather forecasting. And I'm constantly amazed at the innovation. We used to worry so much about using computers totally efficiently. Like weather prediction has gotten so much better, and it got better for a variety of very insightful things, but several things that are very insightful that made weather prediction better are actually very computationally complex. So people with imagination said, well, what if we do ensembles? What if we do analysis of satellite photos to reverse engineer data? It's a few brilliant ideas thrown in modeling that are only possible because of the immense amount of compute power. And weather prediction is worth a lot of money. And it's very, very important to people to have accurate weather. Can help with shipping. It can help with armies. It can help with aircraft. It turns out there's a lot of benefits to having good weather prediction, even emergency reactions, figuring out better and better where a hurricane's going to land and mobilizing people. And so there's been a lot of money spent around the world just on, say, weather prediction. Of course, you can say the same thing about drugs and pharmaceuticals and computations about the spread and cures for COVID and so forth. They've all are very computationally intensive these days.
Mm-hmm. Mm-hmm. So you've been involved in the creation of several of the world's fastest computers. So what it takes to design a supercomputer? What are the challenges?
It's a very disciplined engineering task. Let's say you're imagining that you want to build the world's fastest supercomputer 3 years from now. It takes extraordinary people to be very disciplined at paying attention to all the different factors. What can you build? What software can use it? What technologies will be available to you? Obviously, you want to use in general the best technologies available at the time that you build the machine, but best doesn't mean just fast. It means deployable. It means reliable, serviceable. So it's, there are a lot of wild ideas about architecture out there, but when it comes time to actually build a machine, you have to actually make hard choices about what can we build. And often you find yourself looking at it and going, gosh, if I only had one more year, there'd be some new technologies I could incorporate. But you don't have that luxury. You have to actually sit down like engineering any other thing, an aircraft, a car, whatever. You actually have to build it with the technologies available to you at point in time. It's a fabulous undertaking, and nowadays it's not just one brilliant architect dreaming it up. It's a lot of people working cooperatively together. There's often a lot of studies because you'll sketch out on a board, well, what if we had 9 of these on each node versus some, and then you actually spend a fair amount of time doing simulations and so forth ahead of time to figure out if your workloads, which ones will, how well will they scale, how well will you use the machine, because you really need, when you deliver that machine, to be able to take advantage of it with a lot of workloads. And tying it back, the question that was asked earlier is like, who buys these things? I said it was universities and stuff. The other thing that's interesting is these machines need to be versatile because they're usually not bought for a single purpose. The biggest computers in the world aren't bought to do one workload. They have to be good at a lot of them. And different workloads behave differently. AI workloads are different than chemistry workloads, are different than physics workloads, and so forth. And then you have ones that combine all those techniques that you want to work well. And it's gotten a lot more complicated to decide what architecture will do it, but versatility isn't.
Mm-hmm. I wonder. I wonder how do I deploy? So let's say I wrote some scientific program that I want to run on one of those beasts. So how do I deploy and run this software? So assume that I, for example, reserved 1 hour on this machine. So how do I do I have to care about all the parallelism myself, or there are like existing programming models that can that I can leverage?
If you're going to use an entire exaflop machine, which, by the way, very few programs run on an entire machine, because you partition the machine, and at any given time there may be dozens or hundreds of workloads running on a machine that size. It's very uncommon to use the entire machine for one application, because each node, if an application is using a node, it's dedicated to that application, for a variety of reasons. It's for predictable performance and it's for security. But so your application scaling, even if you're going to use 1/10 of an exascale machine, your program needs to scale pretty darn well. So what you'll quickly find out is if you get time on a machine like that, the people that will work with you who manage the machine are going to want you to prove that your application scales. So they might limit you to 10 nodes or nodes and force you to show that your program is scaling, because they don't want to give you 100,000 nodes and find out your program used 10 of them. That's a huge waste. So it's pretty amusing talking to the folks that manage these systems, because they some just amazing people who help scientists and so forth, and those of us that are programmers take advantage of machines. They've learned the hard way that they need to talk to their users about their workloads and help them demonstrate that they're scaling. And before you give them, the opportunity to run on 10,000 or 100,000 cores, you make sure that the program is scaling, and then you'll find that they're eager to share their expertise and talk to you about tools and so forth. But that's the experience you would have if you got time on one of these big supercomputers. You would quickly find yourself with some people that were there to help, that were first trying to figure out whether you knew what you were doing and how much help you need to get your program to scale before they turn over a bunch of these cores to you for very long.
Okay, so I actually also, okay, well, we're here on this topic. Okay, our guest Chad, you can talk now.
It's an honor to talk to all of you. I'm Felipe James and Denny. I was listening to this. I work a lot with like Lawrence Livermore and Sandia. I'm a PhD student here at the University of Oregon with Al Maloney and Shamir Sinde. I think about supercomputing is like sort of understood often by the kind of workload it's designed to solve. I wouldn't use a supercomputer to run Excel or to browse Twitter, but you use it for certain kinds of jobs. And the multiple node aspect is one of the ways in which the supercomputers are addressing issues with scaling, where you don't just have one bigger core or one big chip with full RAM on one device. You can have parallel access to parallel banks of memory, and then you have access to them by kind of dividing up your workload across those multiple nodes. And that creates an architectural difference that's inherently different from a very, very powerful individual workstation. And there's always, when you were answering that question about designing the supercomputer, there's always a kind of software and hardware co-design that happens at the same time. So if you're going to field a new machine for those three, not only are people looking at supply chain, can we get these chips? Can they be manufactured through the network of fabs around the world? And how do we tie in all of the timings of various parts of this machine so that you don't have that stalling baked in all over the place? But you also have to have these software toolkits so that you can address these new capabilities. And you may have 6 million lines of code in a physics simulation that has thousands and thousands and thousands of different kinds of parallel regions. And you can't go and port all of those lines of code to a completely novel architecture. You need to have some way of mapping that problem onto the new asset, the new hardware asset. So that kind of programming to an abstraction, you can have this awesome machine, but it's going to be dark silicon if you can't run a program on it. So I was going to ask to hear what your thoughts were on those sorts of techniques and how maybe like Intel One API is helping people use the supercomputers, and maybe what you think about the kind of back and forth, push and pull, the tension between developers and the software abstractions and then the hardware engineering that underlie them. Like, are we constraining our imagination because of legacy codes, or how do you see all that interacting, I guess? But thank you again for this talk. This is fascinating.
You brought up a number of interesting things, so let me take them. By the way, fabulous place to be going, University of Oregon, and Alan and company, fantastic. Of course, you've got Samir there with Tau, so a lot of great things going on there.
Thank you. I'm very lucky.
Yes, take advantage of it. It's great. The one thing you touched on a little kind of triggered is one thing you could ask is, what's the difference between a supercomputer and a data center? It's very funny. Supercomputers are really about throughput. How much computation can I do a second? Because I'm going to give it a really intensive problem. Whereas data centers are very optimized for latency, meaning that you want to connect to tens of thousands, hundreds, millions of people around the world, and you want to be able to react to them quickly, whether it's a Google or a Facebook lookup or something like that. It's enough of a different design that it's a fascinating design trade-off. But you were asking the question, how novel can you get, essentially? And this is a thing that always challenges a designer of any new mousetrap, right? No matter what you're doing, if you design a great car, but it can't drive on the streets that we have today, it's who are you going to sell it to, right? The same thing's true of computers. If you look at NVIDIA and the introduction of their GPUs and CUDA into HPC, they had a fantastic hurdle at first, and the early successes centered around things like cuBLAS, which was basically a linear algebra subroutines. And what people first did with the GPU, in a lot of cases, was just link with a different math library to run faster. And yeah, they had to do a little tweaking to their program, but it's fundamentally, if you're going to design a new piece of hardware, you have to have an on-road, right? You might convince people over time to use novel features in your hardware, but you also have to answer the question, what am I going to do with my existing code, at least quickly? A very large amount of code in scientific world rests on top of BLAS, matrix multiply, maybe FFTs, things like that, solvers. And if you have a good implementation of those and you can make them run, that's traditionally been the way to prove that you're worth buying in the HPC market. And then if you have something novel to add to that, people can run their existing code using those on-roads, and then they can play with the novel stuff. AI is giving us another dimension, which is, how fast can I train? How fast can I do inferencing? And so things like TensorFlow, give a lot of startups basically talk about how much they can make TensorFlow run faster. That's their magic on-road. So, as engineers, that's a critical question when we come up with brilliant new ideas. You have to answer the question, how are you going to help existing people? You really limit yourself too much, probably, to make it in the world if the only thing you can do is crazy novel things nobody else can do. That doesn't mean you can't do it. Maybe you would argue quantum computing's in that domain, although I'd say quantum computing, when it hits the scene in a big way, is probably going to have a class of applications that we do today that they just do much faster. That's going to be their on-road. It may be physical system simulation probably for quantum computing. So answer to that question, absolutely. So when you look at FPGAs or you look at TPUs or something like that, you have application. You have to make it easy for an existing application to somehow take advantage of that. No matter how novel your idea is, it needs to accelerate existing workloads. And they go back and forth. Because nowadays, I said that NVIDIA started with cuBLAS, but nowadays a lot of applications have been refactored and understand how to offload their workloads to a device, to a GPU. That didn't exist 10 years ago, but applications react to the hardware. A lot of code today is for vector computers because of Cray back in the 70s and 80s. And machines since then have looked like that because the codes were modified to take advantage of the hardware. And that process continues. Workloads evolve because of the hardware, and hardware evolves because of the workloads.
Awesome. Thank you very much. That's a great answer. Do you want to talk a little bit about maybe what's happening with like Intel One API? And I've worked a lot with Kokos and Raja as parallel portability layers as ways of abstracting out some of the things that these architectures provide for us, so that newer machines we can sort of automatically start gaining advantage from them. But I think SYCL is kind of the future in a lot of that. Do you want to talk about that for a moment? And I'll dip out.
Yeah, absolutely. I mean, this is near and dear to my heart. it's, you know, Cocos and Raja are projects in the national labs that, you know, and SYCL is a standard, and One API is an initiative Intel's been promoting as an open initiative. We're all after the same thing. We have different takes on it, but the reason that all these conversations, all these projects are starting is because we see a future of a lot of diversity in hardware, and we're trying to say, what is the abstraction we program to that allows us to survive this? Because, you know, you can get very excited about diversity in hardware and so forth in the future, but you can't afford, if there's going to be, you know, 20 new novel architectures next year, we can't refactor our program for all 20 of them. So the question is, what can we do to make our applications ready for this diversity, but ask that the hardware support it? The way I describe One API, well, it's not one and it's not an API. It's the question is, if I'm trying to do something like an FFT, how many interfaces do I need to learn for different hardware? And I would say, look, FFTW came along a while ago, and I think most people use that interface. And if you look at BLAs, you know, basic linear algebra subroutines, those routines are similar. So if you generalize that, you can say, well, why don't we design our software, our libraries, our compilers, with the idea that they need to be able to handle diverse hardware? Why don't we start with that as a design concept? So if you've got a brilliant idea for a new library, I would say shame on you if the library is only for a GPU, or it's only for an FPGA, it's only for a CPU. Why don't you write the library in such a way that it can adapt to different hardware, or at least that the interfaces, as to the best of our ability today, that the interfaces are designed in such a way that they don't force you to one particular style of hardware. Now, I still want the performance, so this is a pretty tall order. It's not, this is not a write once, run everywhere. This is a fascinatingly complex engineering problem. But SYCL is looking at how do you add kernel-based programming in general to C++, but do it in a way that doesn't assume that you know a lot about your device, compared to CUDA, which is written with the, well, I know that I'm targeting an NVIDIA GPU. And you know what? They're interesting design trade-offs when you look at one or the other. Obviously, if you can know more about your hardware, you can supply one type of interface. And if you know less about your hardware, you have to generalize it a bit and add queries and things like that, and capability feedbacks or capability queries. But I think that's where we need to go. We need to have more of our software support arbitrary devices, you know, and that's a big change for compilers, for instance. The idea that a compiler needs to be able to interact so that it can produce code for arbitrary numbers of devices instead of all being packaged together. There's the DPC++ project to implement SYCL is done in LLVM. And LLVM is a fantastic place to be, with SPIR-V as the intermediate code. You know, someone can write a SPIR-V backend for their XPU and then use a front end that produces SPIR-V. And you know, with a little work, we're going to make all this stuff just glue together. So it's a very different world. And Raja and Cocos, obviously for the labs, are trying to solve this problem of can we let our scientists write code once and then it can run on whatever hardware these different vendors will produce for us? Because we'd like to be able to buy, you know, if you're a national lab, whatever hardware looks the most exciting to us, but we don't want to have to rewrite our code every time we buy a new machine. So we're all having that same conversation, and I think One API is a fantastic effort to sort of up the game, build some more specs, especially in libraries and tools. Compilers is important, but libraries and tools are incredibly important to have this discussion. Why don't we assume that when we write tools like that, that they're supposed to handle XPUs in general, as opposed to always being specific to one? I think that's the big revolution that's underway, and I think One API is a very critical part of that revolution.
I think there is like one important message that you said that should be passed to all the library implementers, which is that they should design their libraries like to be heterogeneous from the start. And I think that's really cool idea. But since we already started talking about SYCL and DPC++, and you already talked a little bit about the high-level vision, but let me just bring you back to the basics. And can you like shortly describe what is SYCL, what is DPC++, and how the, let's say, the mainstream developers can try it?
Yes. So SYCL, a little history of it. So there have been a variety of different kernel-based programming languages over time, inspired mostly by GPUs, and CUDA had risen to be very popular. Obviously, OpenCL was, if you will, another one that was more open. But OpenCL is pretty low-level oriented, and the people who worked on OpenCL at a C++ interface, a little higher level, more general, was a good idea, and that's where SYCL came from. But it's taken a while, with a lot of industry input to figure out how to generalize kernel-based programming. Ultimately, what it does is two things. It provides an interface to query what's on my machine. So when your application starts, you can say, hey, can you find me a GPU? Can you tell me about the GPU? Does it have coherent memory? You can do all sorts of queries, or you can just say, hey, I want an accelerator, whatever the best thing on the system is. And then you can dispatch work to it, and you do that through a queue. Specify a kernel, either a function or a lambda function, and you say, I want to dispatch this to the hardware. And then magically the compiler compiles that part of code, and SYCL lets you manage that. So you're able to find the devices and use them. And it's done in a very consistent manner with C++, which is interesting. So it's exciting. So that's what the SYCL standard is and it's implemented by different vendors. And the DPC++ is an LLVM project to implement it in the LLVM world. And I think it's gaining a lot of attention. It's obviously going to be one of the programming methods used in the exascale computers, at least the ones that have Intel hardware on them. And it's showing really good results on AMD and NVIDIA through some work code plays done. I've seen some RISC-V and some ARM ports, some stuff with Huawei's AI chip. It's a very interesting, there's going to be a lot of attention to it because it's a standard. If we get behind, it stands the chance of giving us kernel-based programming on arbitrary number of different devices from many different vendors. So that's a slice of the puzzle, right? Because kernel-based programming is one facet of the world, and you can ask, well, how am I going to get MPI? How am I going to get OpenMP, Fortran, Python? They all have similar answers, but SYCL is all about kernel-based programming in C++.
Mm-hmm. Yeah. So let me ask, what are the advantages over OpenCL? Because, well, in OpenCL, you write separately host code and separately write the kernels. So what are the advantages of SYCL here?
There's two advantages that I dwell on, and there's probably more, but one is what you mentioned. It's single source, and it was a huge advantage to be single source so that you look at your code, your programs, got host code, stuff that's running, and suddenly there's a device. Being able to see that in a common flow is very powerful. There were two, there's actually three things. The second thing is composability. For whatever reason, OpenCL has two levels, and so it turns out it's really difficult to incorporate OpenCL in a program. To me, composability is I can arbitrarily mix things, and so it turns out with OpenCL, if you use OpenCL in a library, but then you use it in your program and you call that library, bad things can happen. And it turns out this can happen with OpenMP also. But if you design things right, like TBB and so forth, you really can get a level of composability, and that's important because I don't really want to worry was SYCL used in a library when I call it. I don't want to have limitations. I want to be able to mix them. And then the third thing is integration with C++ is critical.
Right. So let me ask this question, let's say, from the perspective of the mainstream developer. And then, so suppose that I have like my program, right, written in C++, and I think, well, I mean, and it is very much like easy to reason about the sequential program, right? It is a little bit harder. I mean, at least for me, it is a little bit harder to reason about in terms of, in terms of SIMT model, right? So, like, AKA shader style programming. So, um, oh, what do you like? Will it be a hard sell for a mainstream C++ developer to like rewrite their sequential program like into SYCL and DPC++?
Well, so there's kind of two things you're mixing. So first of all, we had the discussion before. How do you onboard hardware? So if you're already using GPUs and so forth, you're likely to be using a kernel-based method, CUDA in particular. And so SYCL gives an on-road for that. So it's music to people's ears that have been looking for a method to keep using their CUDA code. On the other hand, if you're a C++ programmer, if you're going to use parallelism, you're going to need to refactor your code, or you're going to need to do something. The good news is there's lots of techniques. I wouldn't promote OpenMP to C++ users in general. It works better with C and Fortran because of composability. But threading building blocks is there. There are other people with other libraries and so forth that try to support. You're really free to use whatever method works for you. But kernel-based programming is pretty popular. I think a C++ programmer that's worried about parallelism is probably already using a parallelism technique. And in general, those will have some support on the hardware. Some of the things like executors and stuff in C++, it remains to be seen how effective they are if you scale out a lot. But they give you some inroads to these things. But if you're a C++ programmer that's still stuck in the serial world, the first thing you have to do is figure out that you're going to have to change your program for parallelism.
Mm-hmm. That's fair. So we also talk about those heterogeneous libraries, right? So will it be fair to like envision this situation where like there will be heterogeneous libraries, right? So for example, like video encoding, and then so which will run under the hood, right? So I don't have to care like exactly like so I just call those APIs, and then this stuff runs automatically, like with offloading to all the accelerators, right? So
Absolutely. Libraries are in general a way to use hardware. The challenge with libraries is if your hardware is distinct and you have to move data to it, you need to have a problem, right? You can't have little 3x3s to do one at a time. You have to give it a lot of work. And Amdahl's law will come into play when you each time you send a library worth of work to do, and you have a pause before you send it more work, Amdahl's law will start to kill. There's a lot of different things. Sometimes you don't care. If you're writing Photoshop, the user is doing something and you want it to do a quick transform, and then the user is doing something, you don't care about the Amdahl's law as much. But if you're trying to do a lot of throughput, you start getting into you have to design your program to overlap so that you're initiating a library call and moving data to get it ready while the last library call is finishing. And some of the parallel libraries provide mechanisms to do that. And that's one of the things you have to learn to get the maximum throughput. If you're using libraries, which I think is a great idea, you still have to reason the overlap of communication that's moving data and computation. You have to get them to overlap, or else you won't get the as much speed up as you may want to have.
Mm-hmm. So going in 10 years from now, do you think that like we all will be like a heterogeneous developers? Like so.
Yes. Yes. In one way or another, today we're all parallel programmers. In one way or another, you have to realize that the hardware we're running on today is parallel, and you may not program it directly, but you're working in a parallel world. Something that you're interacting with, maybe connected to the internet, and you're doing parallelism that way, exchanging data with a server, or you're running on multiple cores, or you're interacting with the OS that's running on other cores. So we all have to worry about a little. In the same sense, in 10 years from now, we're all going to have some of heterogeneity. Some of us will be programming it directly like crazy, and others will just be living in the world of it, but you can't remain ignorant of it and be as good of a programmer as you would be otherwise.
Okay, so let me go back to this question. So do you think this will be it will be hard for to shift the paradigm from sequential programming to kernel-based programming?
I think kernel-based programming is another tool in your toolbox, right? It's just like, so people may specialize in using Python or using OpenMP or using TBB or using kernel-based programming. I don't think everyone has to understand or use any one of these particular tools, but be aware that the tools are there, and the most versatile programmers will understand for different problems they have to use different tools.
Okay, cool. So one API and SYCL are open standards, right? So what are the benefits of of being open here?
I'm sorry. Yes, standards are critical. Was there a different part of the question?
Yeah. I was just wondering. So like CUDA is proprietary, right? So while SYCL is an open standard, right?
Yes.
So what do you? Well, maybe the answer is obvious, but what are the advantages of making this open standard? So what are the advantages of making this standard being open? Yeah.
Well, so closed has a couple of problems. One, if you're trying to support a closed standard, you're chasing the standard, right? You're not part of setting it. So you're usually a few generations behind, and that's what you'll see with people that are trying to support CUDA. They're generally a few generations behind, like AMD's HIP and ROCm support CUDA 7 and 8 pretty well, which is great. And but supporting the latest and greatest is hard when the standard's being set by somebody else for their hardware. The other thing is it's limiting to innovation. So if companies can come together that have different ideas and affect the standard together, like Fortran or C++ or Python, look for equal footing so that their hardware has a chance. Whereas, if it's proprietary, you just don't have that opportunity for innovation. So I see standards tend to open up a lot of innovations and give us surprises and upsides for all of us in terms of what our future computing looks like.
Okay, cool. Well, it's
been a pleasure. This has been great.
Yeah.
Hopefully we can carry on the conversation in the future, and hopefully people have gotten a lot out of the discussion. Look for any feedback if there's more stuff on Discord or if there's more opportunities to follow up on this in the future. This is a topic near and dear to my heart.
Sure. Thank you very much. Yeah. So the live chat was actually quiet today. I don't know why, but yeah. Well, James, thanks. It's really a pleasure for having you today. I personally have so many insights. Really, thanks for coming. And to all the folks in the room, I would love to see you join us next time. Yeah, see you in 2 weeks, and happy performance tuning.
Thank you all.
Thank you. Bye.